This is MATHguide.com. My name is Mark Karadimos. Today we're going to take a look at the Binomial Theorem, and we're going to learn how to find specific terms in general Binomial Theorem expansions. Alright, in this video there will be three sections. Section 1, we're going to talk about the connection between Pascal's Triangle and combinations. Section 2, we're going to bring up our first example. Section 3, we're going to talk about our second example. Alright, let's get started. This is Section 1. We're going to talk about Pascal's Triangle and its connection with combinations. Alright, well, first of all, let's look at Pascal's Triangle. So Pascal's Triangle, which does look triangular, you can see the ones here on the left side, ones here on the right side, forming this triangular shape of numbers. Well, to find values in this triangular pattern, you just take two adjacent numbers, you add those numbers, and take the sum and write the sum underneath. Okay, like for instance, I would take 1 and 3, I would add 1 and 3, I get 4. I could take 6 and 4, I would add those two numbers together, and I would get 10. Okay, so you can see that's how these are formed. And if you want to continue on the pattern, you just have to place ones here on the outside. And again, you just have to add. Add, I get 6, add, I get 15, add, I get 20, add, I get 15, add, I get 6. Okay, without getting into more detail about this, in our previous video with expansion, Binomial Theorem expansion, I go into more detail about the Pascal's Triangle. Well, in this section I want to talk about how Pascal's Triangle is related to combinations. So in calculators that you use, there is a combinatorics feature, and we could use the combinatorics feature to reproduce rows within Pascal's Triangle. Like for instance, if I wanted to reproduce these numbers 1, 3, 3, 1 using combinations, I would take 3, choose 0. I would take 3, choose 1. I would take 3, choose 2, and I would take 3, choose 3. And if I plug this into a calculator, this one right here, 3, choose 0 is 1. 3, choose 3 also turns out to be 1. 3, choose 1 turns out to be 3. 3, choose 2 turns out to be 3. So you could reproduce these numbers using combinations. If I wanted to reproduce the next row, okay, I would just have to use a different value. I'd say, okay, this is now 4, choose 0. I would take 4, choose 1. 4, choose 2. 4, choose 3. And 4, choose 4. Okay, so if I did use a calculator to calculate these values, I would get 1, 4, 6, 4, 1. And there you have it. I would get those. And I can continue on. You'll notice the pattern is I start with the value 4, and I got to choose 0 as my first term. Okay, so 4, choose 0, 1, 2, 3, and 4. And that's how I find it. So it turns out that even though you're choosing, or you're taking 4 items, you have to choose 0 to receive your first value. And you'll notice that there's always one more than the value you're starting with here. This 4. Interesting patterns going on. Anyway, this is going to help us when we do our problems with Binomial Theorem expansion when we are looking for specific terms, as we'll see in the next section. Alright, this is our second section, and we're going to get to our first example. Alright, in this example, we're going to talk about what it would look like if we took the value 2x plus 1, which is a binomial, and we raised it to the 8th power. Okay, let's say we raised this to the 8th power and we wanted to expand it, but we're really only concerned with the 6th term. just the sixth term. I don't want anything else. I don't want the first, second, third. I don't want anything other than just the sixth term. Well, generically, if we were to take a plus b, my generic binomial, and we were to raise it to the 8th power, let's just look what the expansion would look like. Okay, this is necessary for finding patterns. So the highest power we're going to get for a is 8. We're going to get, our next would be 7. And you can see I'm just dwindling down by ones as I continue on. Okay, so I get 8th power, 7th, 6th, 5th, and so on as I trail down. Dot, dot, dot. Okay, what happens with the b value? Well, the b term, there's going to be no b's here. There's going to be one b there, b squared. You can see now the b's are going up in power. Okay, so that's one pattern. Okay, the other pattern that we have to get into is finding the values that are in front. In other words, the coefficients. All right, I'm going to move this equal sign. I need a little bit of room here. So each one of these terms has a coefficient. So to find this coefficient in front, we're going to use the combinations we just were talking about in the previous section. So we're going to put 8, choose 0. We're going to put 8, choose 1. We're going to put 8, choose 2. And so on. 8, choose 3. And we're going to go on there. So there would be plus signs, obviously, in between, because these are terms of a really large polynomial, large complicated polynomial. All right, well, let's find some patterns so we could see them, use them to figure out the answer here to this 2x plus 1 problem. All right, well, you'll notice that one pattern is that the power on the powers on the variables always are going to add up to 8. So here is b, you don't see the power, it's a power 1, but if I add 7 and 1, I'm going to get 8. If I add 6 and 2, I'm going to get 8. If I add 5 and 3, I'm going to get 8. So every term has a degree of 8. Okay, that's one pattern. When we take a look at our combinations, we could see that the front number is always 8. Okay, it's always going to be the power to which we're expanding. Okay, what's the second number? Now the second number, well, there's an interesting little pattern here. If I say that this is my first term, second term, third term, fourth term. Okay, so if I start labeling these by term number, you're going to see another pattern. That when I say that this is 8, choose 0, notice the second number is always 1 less than the term number. So here I've got my term number 2, but that number is 1. Term number 3, but that number is 2. So there's a pattern there as well, a very simple pattern. And you also could see that whatever the second number is in our combination, that second number always matches the second power. The 3 matches the 3. The 1 matches the 1. A lot of interesting patterns going on, and that's what mathematics is all about, is finding these patterns. All right, now I want to find the sixth term. Okay, so if I want to find the sixth term, I'm going to put down a combination. I'm going to put down a and b. So I need to know the two numbers of the combination. I need to know the two numbers of the power. Now, keep in mind that this is the sixth term of what I'm looking for. I'm looking for the sixth term. So if we were to just continue this pattern, we would say, okay, the first number is always going to be the power to which we're expanding. Okay, the second number of the combination is always 1 less than the term number. See the 2, 1, 3, 2, 4, 3. So I know this is going to be 1 less. I know that this second number is always going to match the power on the b. And I do also know that these two exponents are going to add up to be the power to which we're expanding. So that has to be a 3. All right, so this is what the term is going to look like. All right, so the last step, we are now going to substitute. So we're going to put in our a and our b. Now we know that the a is really just equal to 2x. So I'm going to replace that a with 2x. And we do know that the b is equal to 1, so I'm going to replace the b with 1. All right. So in a calculator, I'm going to put in 8 choose 5. It's 56. I'm going to put in 2 cubed. That's 8. Right? 2x times 2x times 2x. It's 2x cubed. And 1 to the 5th is just plain old 1. So when I'm done multiplying all this together, really just 56 times 8, I get 448 x cubed. And there's our first answer to our first problem. All right, let's go on to another problem. All right, in this second example, I'm going to move a little bit faster so that I can show you the pattern a little bit quicker. Now, we're going to take a little bit of a harder problem, 3x minus 4, so we're getting a little bit more technical with negatives, and let's put a ridiculous exponent. Now, I wouldn't want to expand this all by hand. It would take way too long, and we only want the 7th term. Okay, again, we start with our generic expansion with a plus b, or use 2 other letters that are not x. And let's use the expansion. So we're going to use a to the 18th, a to the 17th, a to the 16th, a to the 15th, and so on, dot, dot, dot. Okay, what's the b doing? There's no b's. There's b to the first, b to the second, b cubed. Okay, what's our first term? It's going to be 18 choose 0, 18 choose 1, 18 choose 2, 18 choose 3, and we'll put plus signs. Okay, we only want the 7th term, but it's important that we see the connection between term number. Where are we? There we are. It's a big blob of letters and numbers. Here's our 4th term. So what do we want? We want the 7th term. So let's find some connections for term 7. All right, so in our problem, there's going to be a combination, some power of A, some power of B. The 18 is going to be our combinations. That is the expansion to which we are looking for. So let's see. Notice that the term number, well, this number is always 1 less than the term number. So that's got to be a 7. 1 less is 6. We know that this, well, let's go to this term 2. We know that this second number always matches the power on the B. The 2 always matches the power on the 2 there. See that? They always match. So let's see. If that's a 6, this has to be a 6. Since it's the 18th power, I know that all the powers have to add up to be 18. So 6 plus 12 is 18. And there you go. This is what the generic term looks like. So what am I going to do? I'm going to start putting in some values. So let's see. I'm going to replace the A with 3x. I'm going to replace the B with -4. I'm going to throw this value into a calculator. Okay. Okay, let's see. So this number does turn out to be big. It turns out to be 1856.4. I'm going to put 3x to the 12th power. So that's going to also be a large number. 531,441 x to the 12th. I'm going to put -4 to the 6th power. Another large number. 4096. This is huge. Yep, this turns out to be a ridiculously large number. So now I'm going to multiply all those numbers together. And we're going to get another huge number, 40, 409, 787, 285, 504, x to the 12th. Okay, so we get this large number. This is our answer. This is the final answer to this problem. This is a huge number. That would be thousands, millions, billions, trillions. This value right here is about twice the national debt. So anyway, we have our answer, and that's how we expand binomials for specific term numbers. All right, make sure you go back to MATHguide.com for more math education, more instructional videos, interactive quizzes, and of course, text-based lessons. Take care.